Good morning and welcome to Computer Science 221. We're going to start talking today about Chapter 9. In fact, we're going to be in 9.1 on this particular video. We're talking about the trap mechanism. Okay. First of all, I want to recall a couple of things here. A trap that we've used before. We've used this trap 23, which is sometimes referred to as just plain old in. And remember what this does. This actually prints a prompt. You know, it says, I think it looks like this, and it says enter a character. So it does that, then it gets keyboard input. And then finally it also echoes to the display. It echoes the input up on the display. So it does all of these things. And again, I do want to remind you that we actually wrote the code to do this in Chapter 8. So basically what we did in Chapter 8 is we wrote most of the code that implements this trap right over here. So there are a couple of things to note. Some things to note. Okay, important things to note. Number one, it was long, complicated code. And the reason why I mention that is as follows. In programs that we write, there may be lots of situations where we are getting input from the keyboard. And remember, all this did is this input, just one character. But we wouldn't want to repeat that code every time we needed another character. So we wouldn't want to repeat this. We wouldn't want to repeat this every time we wanted a character. There may be lots of times in our program where we want the effects of this, but if you recall when we wrote this, I seem to remember it was about 20, 30 lines of code. We wouldn't want to be repeating this all the time. We would like some convenient way that we could invoke the effects of this without having to rewrite the code. But here is another point here, and this is the really, really important one. You may recall that when we wrote this thing, we had to access these I/O registers. And in fact, we had to access the keyboard status register. We had to access the keyboard data register. We had the display status register and the display data register. Okay, these are device registers, and these are very, very important. Here's the thing to think about. Maybe we're working on a computer that's multitasking, such as the computer that I'm working on right now, my Apple, or maybe we're working on a computer that's multi-user. There are lots of users using the same computer. We don't want people having the ability to tie these things up. We don't want to give individual programmers the ability to go in and start playing with these registers, because that could then impact how other people are able to use the thing. So these are sometimes what are referred to as privileged. These are privileged instructions. They're privileged memory locations. We want to restrict access. Okay, now the whole idea of making things privileged is a very, very complicated topic, and we'll leave most of the discussion for that to a class in operating systems. But here's what we would like. This is the whole idea of the trap mechanism. Here's computer memory. And here's my code. And what happens is that someplace over here, here's code for input. In fact, maybe what's over here is this may be the code that is in fact trap 23. Okay? And at some point here in my program is I would like to get a character. So here I am over here. So the idea is what I would like to do is I would like to, at this point, I would like the execution of the computer to jump down to here and start executing this code. Now this code ends at some point. Let's say it ends here. So I'll put X's there to indicate that it ends. So I want to go from here, I want to jump down to here, okay, and from here I want to start executing this. And then when I get down to this very last statement here, I want to come up and I want to get over to here. The next instruction, okay? And again, you can imagine that maybe later on in my program, maybe again I want to get a character. And the idea is the same thing. From here, I want to jump down to here, and then I want to execute this. But now when I hit the last instruction here, instead of coming back to here, I want to come back to there. Okay? So I think you can see what's going on. So basically what I'm going to say here is that the trap gets us to the code. And then the other thing that we have to be concerned about is what's called the return mechanism. In other words, once we hit this last statement, how does the computer know where to transfer execution? And we saw that in one situation, it should transfer execution back to here, and in another situation, it should return execution over there. So these are the two things that we have to worry about. Okay, so first let's talk about the trap mechanism. So first of all, we know that there is this trap instruction, and the trap instruction looks like this, and then there are 4 zeros, and then over here there's an 8-bit trap vector. So in our case, when we said trap hex 23, it was 1, 2, 3, 4, 1, 2, 3, 4, and then there's a 2, 0, 0, 1, 0, and then 0, 0, 1, 1. Okay? So the question is, what is this doing? And now we will describe the answer. So the first thing that we need to know is on the LC3, we can have a total of hex 0 traps. Okay, so first of all, that number right there, you should recognize that's 256. Base 10. And those traps would be numbered from 0 all the way up to like that. And the one that we're looking at over here, the one we've been talking about, is this one called 23. Now the thing that you need to realize is that first of all, not all of these may be in use, okay? But let's not pay any attention to that. But we know that when we look in the book, we saw that there were these traps 21 through 25, and they had particular functions to them. So the idea is that each one of these traps over here does something. So the other thing that means is that each one of these has some code associated to it. And the idea is that if we have this computer, and you can imagine that the computer has some disk drive, and please excuse my very simple drawing here. Here's a disk drive where the operating system is stored out here on disk. And again, I tend to think of a disk drive as almost like a record. Do you all remember what a record is? And what happens is that the code for these various traps lives on very specific places on the disk. So for example, from here to here, that might be trap 0. And from here to here, that might be trap 1. And from here to here, that might be trap 2. Now, what happens when you boot the computer up, the computer knows in the booting process it has to go to very specific places here on the disk. And what it does is it knows where these traps live. And it comes over here. Now here's computer memory. And I hope I have enough space to demonstrate this. It's going to come over here and it's going to read the code for trap 0, and it's going to load it someplace in memory. So it's going to come over here and it's going to go, oh, maybe starting over here at hex 1000. Here's the code for trap 0. Okay, but now what it's going to do is it's also going to come here in low memory, and at location 0, it's going to put in the number 1000. And here's the end of trap 0. And then maybe it comes in and at hex 1200, here it reads in the code for trap 1. And now it's going to go over here in low memory at location 0001, and it's going to put in hex 1200. So this whole thing down here, the first 256 locations in memory, all the way up here, all the way up to 00FF, this is what's called the trap vector table. And you can see that what happens here is that as these different traps are read in off the disk drive during the boot process, they are loaded into various places in memory, and we record where those locations are. So if we come over here, say to 23, because that seems to be the one that we keep talking about, maybe that's at location 2000. And way down here at 2000, so here's other stuff here. So at 2000, here's trap 23. Okay? So now I think we know half of the story here. When I say trap 23, what does the computer do? Well, the computer actually does the following. It says, let the PC get loaded with what's in memory of hex 0023. In other words, what it's going to do is it's going to go to memory location 23, it's going to find this 2000 in here, and it's loading that into the PC. Over here, if we look at this, if this get a character, instead of saying get a character now, we actually wrote trap 23 right here. Okay, what this is going to do is it's going to go into memory location 23, It's going to get this number. It's going to load it into the PC. That now has the effect of now the next instruction I execute is down here where the code for trap 23 is. Everybody with it so far? Good. But there's one more thing that has to happen here now. This is the real trick. Okay? And the trick is where do I return to? In other words, we saw the problem over here. In one case, I called it from here, and when I got to the end of the trap, I returned to this place, the instruction right after it. Over here, again, this is trap 23. I execute this. When I'm done, I came over there. So, first of all, we have to note a couple of things. When I am executing trap 23, the PC is pointing right over here. When I was executing trap 23 over here, the PC was referencing that right over there. So the point is that when I actually execute trap 23, before I load the PC with the new location, I must save the PC somewhere. Okay? So I'm going to say that again. So the first thing I have to do is I have to save the PC. So I know where to return to. And then what I need to do, the second thing I need to do is I need to set the PC to memory of, and I'm going to say in here, trap vector. So the question is where does this so I know where to return to. Pardon me for ending a sentence on a preposition. Save it in, here's the big surprise, R7. Let's see if we can demonstrate that. So here we are back at the simulator. And what I've done here, you can see at location 3000, what I've done is I've just specified trap 23, which it's given me the instruction in. What I'm going to do over here is I just want you to watch what happens when I hit a step. Now, first of all, we can take a couple of guesses here. I'm going to come over here, and I'm going to come back and say, let's look at memory location 23. And at memory location 23, I see 04A0. So let's write this down over here just so we can remember that. Zero, 4A0. And the reason why I say that is now let's go back to location 3000. Okay. So what I am going to do is I am going to hit the step. I'm going to execute one instruction. And my guess is going to be is that we are going to jump to location 04A0. And also I should see the number 3001 stored here in R7. So when I come over here and I hit step, well, look at that. It jumped to 04A0. And look at over here. Here is 3001. It saved the return address in R7. Okay, that's very, very significant. Okay, so let's continue with our discussion here. And I'm going to get this out of the way for the moment. Okay, so what's happened over here, this is the trap mechanism. This is how we get down to the trap. Then the question is how do I return? Well, the answer to that is very simple. There is a mnemonic in there. It's called RET. This would be the last line. But actually what RET is RET, we know this thing. This is a jump on R7. In other words, what's going on in there, you may recall back when we looked at the jump instruction. Okay, so the jump had an opcode that looked like this. Okay, and then there were 3 zeros. And then there were 3 bits for a register. And then there were 6 zeros. And basically, what this has the effect of doing is this has the effect of doing the PC just gets loaded with R7. Okay, and that, do I still have that? When I execute that there, remember, when I execute trap 23 over here, if this is at, say, 3000, and this is 3001, okay, that what happens when I invoke the trap 23 here, 3001 got stored in R7. When I hit the return statement here, okay, that takes R7 and puts it back into the PC. It's going to make it come back over there. So that is the complete mechanism over there. It does mean okay, it means a couple of things. It means that the trap routine doesn't use R7. Because if it did, it would clobber the return address. Okay? Now, the other thing that I wanted to point out here is you may recall in Chapter 8 when we wrote the routine to do the get a character, you may recall that when we wrote the, okay, so I'm going to say over here the code to get a char. You may recall that at the end of the program down here, they had something that they called save R1, and it was block word 1, and they had a save R2, and it was a block word 1, and they had a save R3, and that was also a block word 1. And you may remember that the beginning of the code up here is that we saved the contents of R1, R2, and R3. We saved them into here because in the code here, okay, we used R1, R2, and R3. Okay, and then the very last thing that we did before we finished up here is we restored old values to R1, R2, and R3. Okay, so in other words, when we entered the code here to get the character, we knew we were going to be using these registers. So what we did is that we took whatever contents were in the registers, we stored them in here. We came down in here, we executed the code to get the character and echo it. We were using these registers. When we were all done, we had to restore the old values. So that when we were all done with this routine, we have not apparently done anything to these things. In other words, when you look up the code for trap 23, it says that it's going to return the keyboard into R0. It's going to return the keystroke that you entered into R0. It doesn't say anything about any other registers. So what that means is that you are assuming that you can do something like the following. You can do something like add, R0, well, that's bad choice. You don't want to do that. You could add R1, R2, R3. You could do trap 23, and then you could come down here and do something else. And the assumption is that when I call this trap here, the only one of my registers that is going to be affected would be R0, because that's where a character is going to be returned from doing the keyboard input. And then we also know that we're using R7, because that's holding the return address. But we would assume that whatever values R1, R2, and R3 had here, that they still have those values when I get back here. Well, big surprise. Trap 23 is using R1, R2, and R3. Well, because it's using it, we better save the contents of it before we start executing the code, and then we better restore it. So your author points out there are a couple of ways you could do this if you're a systems designer. One way I could do it is before I make the call to trap 23, I could actually save R1, R2, and R3, and then after I return from trap 23, I could restore the values, or I could do the save and restore inside of the trap. And I think that that's actually the preferred way to do it. Okay? That is the end of this discussion. That's section 9.1, and we will go on to section 9.2 forthwith. Bye-bye.